Hello students, hope you're doing good. I'm Dr. Satyashila S, Assistant Professor from the Department of Physics, RV Institute of Technology and Management, Bangalore. So today, I will teach you a very simple yet interesting experiment to find the Young's modulus using a single cantilever method. So, before I start telling you about the apparatus of the experiment and the procedure of the experiment, let us first see what a cantilever is. So, a cantilever is basically a projecting beam which is fixed at one end and it is free at the other end. For all the students who wonder why a certain experiment is done in the laboratory, let me tell you that cantilevers have many applications. Cantilevers are used as cantilever roofs, cantilever balconies, cantilever swimming pools. Cantilevers are also used in the construction of bridges. So thus it is very important to find the Young's modulus of a cantilever. So now let us see what a Young's modulus is. The Young's modulus tells us about the stiffness of a material. It relates the stress to the strain. So stress means the force per unit area and strain relates to the deformation which is caused due to the stress. So basically Young's modulus tells us about how elastic or how stiff a material is. Young's modulus is related to the deformation which is caused under the action of a load. So now let us move on to the different apparatus which we will be using in the Young's modulus experiment. So first, this is a travelling microscope. We have some weights. We have this single cantilever beam setup. So this is the basic apparatus we need to perform this experiment. Now let me tell you about the travelling microscope. So a travelling microscope is so called because you can actually lift the microscope and move around with it. Also, a very interesting thing is that you have two scales in your travelling microscope. So as you can see here, there is a horizontal scale and there is a vertical scale. Both these scales consist of the main scale reading which I am showing here and a vernier scale reading. So this is my horizontal scale, main scale reading, and I will have a vernier scale which is a circular scale. Similarly, if I need to take some readings along the vertical direction, I have a vertical scale. This is my main scale and I have a circular scale here which is my vernier scale. So now as we have seen about the introduction of our travelling microscope, before we start even using the experiment, I need to tell you about the least count of this instrument. So now what is a least count? Least count, as you know, it relates us to the precision of an instrument. It tells us the smallest measurable quantity which we can measure on this instrument. So the least count is also called as LC. So LC is given as the value of 1 MSD divided by the total number of divisions on the vernier scale. So that is how, this is a general formula of a least count. So this is the formula which we use also for the travelling microscope. So now what we need to do is that we need to find the value of 1 MSD and then we need to divide it by the total number of divisions on the vernier scale. So shall we do that? If you look closely at the vernier scale here, my 0 to 1, we need to see how many divisions are there. So in 1 centimeter of my main scale, I need to see how many divisions. So students, let us count together. As you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 centimeter of my main scale has 10 divisions. Yes? So I need to know what is the value of one division. So the value of one division is 1 divided by 10 centimeters. which is 0.1 centimeter. So now I have got the value of 1 MSD, which is 0.1 centimeters. Now I need to know how many divisions are there on the vernier scale. As you can see, the vernier scale is here. So let us look at this vernier scale. Both are exactly same. So as you look at this vernier scale, it's a circular scale, you will see that there are 100 divisions here. Okay. So now my least count is 0.1 centimeter divided by how many divisions? 100 divisions. So what is the value of my least count? It is 0.001 centimeter. So this is the least count of my travelling microscope. So now we have found the least count of our travelling microscope. Shall we now look at the formula of the experiment? So as you can see, the formula of the experiment is the Young's modulus Q is given by 4 mg L cube divided by B D cube Y. The units of Young's modulus is Newton per meter square, where m is my mass producing the depression in kg, g is the acceleration due to gravity measured in meters per second square, L is the distance between the needle and the fixed end of the beam in meter. So let us now see what the L is. The L is basically the distance between my needle and the fixed end of my beam. So we have found out what L is. So we know what L is. B and D are the breadth and the thickness of the beam in meter. Y is the mean depression or bending produced in meter, and this is what we will find using our experiment. Okay. So now we have looked at the formula of our experiment. Now let us look at how the experiment is done, that is, let us look at the procedure of the experiment. So as you can see, we have a travelling microscope here and the single beam here. You can see a needle here. This is our reference point. I have placed a weight W here. So this is my load W. I have placed it here. As soon as I place this on the beam, I find that the needle gets depressed due to the load. Now looking through the microscope, I will set my needle in such a way that it will be at the intersection of the cross wire. So students, we can actually look through our microscope and we will start moving our vernier scale. Now I have set the needle at the intersection of my cross wires. So now let us start taking the reading. As I have already told you, it is we are taking vertical readings, so we will be using the vertical scale. So now through this lens you can actually look at what the reading is. The reading on my main scale is 5. So shall I write 5? So now let us look at the tabular column. So this table shows us the depression for a load of 200 grams. What we do is that I have placed a load W here as I have already shown. Now the reading which I see on the microscope is 5. So I write for MSR 5.0. So as you can already see, the readings are in centimeter. So this is 5 centimeters. I now need to see what my CVD is. If you look closely and you will see that the CVD is 95. So now I will write in the place where it's written CVD as 95. What is MSR? MSR is main scale reading. CVD is coincidence of my vernier scale division. So this is how we take the reading. First, I will keep a load W. Later, for every 50 gram increase in load, I will check what the MSR and CVD values are. Students, it's very important that we try not to move the setup. So very carefully we will try to place the weight. You can hold the load W down and you can set the 50 grams weight here, and after it stops moving, we will start taking the reading. Now, after putting your 50 gram weight, when you look through the microscope, you will find that the needle has shifted. So now what do? We look through the microscope and we will start moving our vernier scale so that it coincides with the intersection of my cross wire. So now after putting each and every 50 gram, shall we start taking the reading? So now I have put a weight of W plus 50. Let me see the next reading. So now I will start taking the readings for W plus 50. It's 4.9 and CVD is 52. So similarly, I will start taking the readings for each and every weight. First, as you can see in the table, first I will take the reading for W, then I will add a weight of 50. So I will get the depression for W plus 50, then I will add another 50 grams weight, I will get for W plus 100 and so on and so forth. I will carry on this experiment till I go to W plus 350. So now as you can see that we have taken all the readings till W plus 350. Now what we do is that we will start load decreasing. For the decrease in every 50 gram of load, we will try to see what the reading is. Okay. So now let us first see. I will remove a 50 gram weight here and I will start taking the reading again. So now you can see we will start taking the reading. Again I will look through my microscope, I will look at my main scale reading and my CVD and I will perform the same experiment backwards. So now let us take all the readings. So as you can see, we have taken all the readings for load increasing and also for load decreasing. So now we have MSR and CVD values. So now let us try to see how we can find the total reading. So TR, which is my total reading, how do I find that out? Total reading is equal to MSR plus CVD into LC. What is LC? We've already found out that's the least count. CVD, as I've already told you, it's coincidence of my vernier scale division, and MSR is my main scale reading. So let me give you an example. Let's take the first one, W. So we have 5 as MSR plus CVD is 95 into my least count, which is 0.001 centimeters. So what is my final reading? My final reading is 5.095 centimeters. So similarly, I will write all my total readings here. So the first one is 5.95. So students, you can similarly write all the readings. Now we have got our total readings. We need to find our mean. So the mean is between my total reading of my load increasing and the total reading of my load decreasing. So students, let us write the mean first. So now students, we have got our mean readings here. Now what we have to do is that you can see in the rightmost corner, we have a column which shows us depression, that is Y, for 200 grams. Now to get the depression for 200 grams, what we need to do is that we take the mean for W plus 200 and then minus it with mean of W. Similarly, we will take the next row here, we will take the mean for W plus 250 minus the mean for W plus 50. Similarly, we will do W plus 300 minus W plus 100, the mean of W plus 350 minus the mean of W plus 150. So students, shall we write down the mean depressions here? So here you can see this is the depression for 200 grams. I need to find the mean of this. So I will just basically add all this and divide by 1, 2, 3, 4. So I have 4 readings here. I will add this and divide by 4. So now I will get the mean for depression for 200 grams. And what is that? 0.5828. This is in centimeters. Now you can see the other data here, M. M is my mass. We have found the depression for 200 grams. So my mass becomes 200 grams. So because kg is written here, I will write 10 to the power minus 3. My G I take as 9.8 meters per second square. The length of the beam, it has already been given to you. So you can see, look here, the L is given as 21 centimeters. So because it's written meters here, I will write 21 into 10 to the power minus 2 meters. The breadth and the thickness have also been given. The breadth is 2.5 into 10 to the power minus 2 meters. The thickness is 0.2 centimeters, that is 10 to the power minus 2 meters. So, the depression, what is my depression y in meters? It is 0.5828 into 10 to the power minus 2 meters. So, now I have got all these values. The simple thing we have to do is now continue our calculation of finding my Young's modulus. So, Q, as I told you, is given by mg L cube divided by b d cube y. If we do these calculations, we will find that my Q comes to 6.22 into 10 to the power 10 Newton per meter square. So, now doing the simple experiment, we were able to calculate the Young's modulus of this beam here. A very important point which I would like to add before finishing the experiment is that now you can see that the Young's modulus is inversely proportional to the depression caused by the load. So, now if more the depression, what will happen to my Young's modulus? My Young's modulus will be less. So, basically the Young's modulus is very low for a highly elastic material, because the depression in an elastic material will be very high and my Young's modulus will become very low. For a stiff material, you will find that the Young's modulus is very, very high. So, now basically I hope you have understood the whole experiment. You have also seen the relation between the Young's modulus and the elasticity of a material. So, I hope you liked the experiment. Thank you very much for listening patiently.